Okay, welcome everyone to the last session of CPP today, which will be about compilers, starting with Jean-Christophe Léchenet on Mechanized Dominator tree certification.
Thank you. So yeah, the context of this work is compilation, and in compilation we have something called dominance, which is quite a central notion, even more with a modern compiler relying on the static single assignment, aka SSA form. It has lots of applications in different analyses. And actually we have a literature about how to compute it and computing the dominance on the dominators efficiently. So as a quick reminder of what is dominance, so in the context, it's a graph theoretic notion, but in our context, we are interested. The graph is a control flow graph. It's a CFG. It has a specific entry node, and we say that a node U dominates a node V if all paths from the entry to V go through U. So here is a simple CFG example. We can note a few things. For instance, the entry node A, it dominates all the other nodes by definition. Here in this case, we can say that B dominates G because the two paths that go from A to G, they go through B. And we can say that C does not dominate E, and for that it's enough to exhibit a path that does not go through C, and we have this red path that avoids C. Okay, and so the dominance has a lot of interesting property. In particular, it's a partial order, it's reflexive, transitive, antisymmetric, but it also has this nice property that it can be stored in the form of a tree, where being an ancestor in the tree means being a dominator. And the parent in the tree is called the immediate dominator. And here it's the dominator tree in this example. But actually, I'm in a more specific context, which is the context of verified compilation. And in this context, the question we ask is how to correctly compute dominators, or how can we have a proof that we correctly computed dominators. And here, the starting point was the CompCert SSA compiler. So it's kind of a fork of the well-known CompCert C compiler written in Rock with an SSA middle end, and it's actually maintained here in Rennes. And in this compiler, there was some work due to Sandrine Blasi, Delphine Demange, and David Pichardy in 2015 to introduce some computation of dominance. So actually, the approach that was chosen was a posteriori validation. So the construction of the computing dominators was not verified, but there was a verified checker. And what they exposed the dominance test, which is like a Boolean function that takes two nodes and answers true or false whether there is dominance, and that shows that this test is sound. And we can already do a lot of things with just soundness, but in some contexts it's not enough. We also need completeness. In particular, in my case, I needed something for a liveness analysis. I really needed completeness. So this was started, this work. And it turns out that in 2016, Georgiadis and Tarjan tackled this problem and proposed a methodology to solve it. So for them, the direct proof is too hard. A posteriori validation, like what Blasi et al. Did, is probably too hard too. So what they propose is that during the construction also comes up with a certificate, a bit like what was mentioned in the talk before the break. But here it's not a trace. Actually, it's a numbering on the dominator tree that has a specific property that they call low-high order. And they give all the ingredients on paper to make this approach work. So they explain how to compute the low-high order. They give a proof that it's a key ingredient to show that the tree is the dominator tree. And they also describe an algorithm to check what needs to be checked on the tree and check that the order is low-high. And actually, in the article, there is this sentence, we leave this task for those skilled in program verification, and this is what we did. So we implemented their approach inside CompCert SSA by extending the previous implementation due to Blasi et al., and it allowed us to prove completeness in addition to soundness. So I will start by explaining what a low high order is and how it relates to dominance. Then I will describe how it was implemented inside ComCert SSA, and I will give some benchmark about how it performs in practice. So Georgiadis and Tarjan, they define two properties that need to be satisfied by the tree to be the dominator tree. The first one is called the parent property, and it's like this. So it says that a parent of a node in the tree needs to be the ancestor in the tree of any predecessor of that node in the CFG. And but the main lemma about this property is that it's sufficient to have soundness, meaning that an ancestor, if the tree satisfies this property, an ancestor in the tree is a dominator, and actually it's the property used by Blaise et al. In the current or former implementation inside ComCert SSA. So just to illustrate this definition, if we take our example and we consider node E, its parent in the dominator tree is B, and we can check that it's indeed an ancestor of the two predecessors of E, which are D and G. So at least for the case of E, the definition applies, but actually it applies for the whole tree. And the second property they introduce is the sibling property, which is like this. So two siblings in the tree must not dominate each other, and intuitively, actually, it prevents the tree from being too flat, because there is one trivial tree that always satisfies the parent property, which is this flat tree, where the entry node is the parent of every other node, and but of course it's not the dominator tree. So if we want to check the sibling property, but for instance here B and H, they are siblings, while B dominates H. So clearly this tree does not satisfy the sibling property. We can try to move B up, but we still have C and D that are siblings, while C dominates D. So we can try the correct one indeed satisfies the sibling property. And the main theorem is that if the tree satisfies both the parent and sibling property, then it's the dominator tree. But checking the parent property, it's easy. It's enough to follow the definition. But checking the sibling property, actually, it involves dominance, and this is what we want to justify. So it's still not obvious how to compute it, how to check it. So that's why they introduce this notion of low-high order. So a low-high order is a pre-order on the tree, and for every node, we need to fulfill either one of these conditions. So either there is an incoming edge for every node V, either there is an incoming edge from the parent of V in the tree, or V has two predecessors, one that is smaller and one that is greater in this order, and the greater one is not a descendant in the tree. But what we can, actually the really interesting case is the second one, but it applies only for nodes that have at least two predecessors, and the other one fall trivially in the first case. So in our example, I annotated the tree with a low-high order, and we can check, for instance, for node F, that indeed it has two predecessors, H and E, and indeed H is smaller than F, so smaller than E, and E is not a descendant of F in D. And so from this low-high order, we can actually construct two spanning trees. I skip completely the details, but what we can finally show is that a tree with the parent property on the low-high order satisfies the sibling property, and since we showed before that the parent and sibling property gave us that it was the dominator tree, we can conclude that what we need to check is the parent property plus a low-high order. Okay, and this is what directs actually the implementation that we did in ComCert SSA. So just the general idea is that we have some very unverified code that computes the dominator tree on the low-high order, and the verified checker verifies that the tree satisfies the parent property and that the order is low-high. And actually, we did that by extending the previous was an implementation due to Blasi et al., which looked like that. So on the unverified part is in OCaml. It computes dominators using one classic algorithm to do so, which is the simple version of the Lengauer-Tarjan algorithm, which dates back to 1979. Then what is passed to the rock side is not the tree itself, it's actually the list of arcs of the tree, which is sorted by a preorder. The fact that it is sorted, it helps for the verification. And on the rock side, it starts by reconstructing a few objects from the list of arcs. So a map that allows to have a fast access to the parent, the candidate dominator tree, and labeling of the tree with intervals. And these intervals, they allow to have fast ancestor checking by just checking inclusion of the intervals. What they check is the parent property, and they expose the dominance test, and what they get is the soundness of the test. So we started from the same thing. On the camel side, now we need to compute also a low high order. So for that, we actually need to instrumentate a bit the Lengauer-Tarjan algorithm, because we needed to output not only the tree, but it's really a light instrumentation, but we need more than just the tree. And you can notice that we have two implementations of the low high order. It's because Georgiadis and Tarjan mentioned one that they proved correct on paper, and one that they just conjectured correct on paper, which is simpler. But since it is in an unverified part, we don't really care whether it's... we don't need to prove it, actually. So we implemented both. And what is interesting, now the list of arcs is sorted by the low high order we compute, but since the low high order is in particular a pre-order, we can do the change to the camel side without changing the rock part, and it still works. But of course, we still have just soundness, so we more or less compute the low high order for nothing. But this allowed us to do the change in 2 steps. But then, of course, what we wanted to do is to update the checker to also check that the order is low-high. We also put more things in the interface. So on top of this dominant test, we also expose now the dominator tree and the fast access to the parent. And now we can prove soundness and completeness. Which is interesting is that actually these were already computed, but they were just used internally. And now we also expose them to the rest of the compiler. Of course, we need more proofs. So all the theory about the parent and sibling properties, the low high order, we formalized it inside Rock, and we proved that indeed it was necessary and sufficient to prove that the tree was the dominator tree. All these intermediate objects, we needed more proofs because they were only the proof needed to show soundness, and now we have completeness, so we need more intermediate lemmas, let's say. We need to prove that the checker for the low high order is correct. Well, actually, it just verifies the definition, so it's pretty straightforward. And since we have more things in the interface, we need more proofs for that also. And what does this interface look like? So actually, when I did that, I didn't have a clear application case, so I exposed some facts. I don't know if this is the ones that are really needed by people in general. But so we have the soundness of the dominance test, the soundness and the completeness. So before we just have the left to right arrow, now we have really the equivalence. We expose the access to the immediate dominator, which is supposed to be the parent function in the tree. So now here we have, we say that the reflexive and transitive closure of the immediate dominator is the dominance relation. And the third point, make the connection between the immediate dominator and the parent, on the dominator tree, and it just says that the immediate dominator is the parent in the tree. And the last one is something more technical, which says that the immediate dominator is defined for any node in the CFG except on tree. Okay, we also did some benchmark to test how this impacts the running times. So we tested on some programs that are typically checked when doing some concert stuff. So we have, so here I gave only the largest program. The second column is the size in the number of lines of code. The third column is SLT, is a simple Lengauer-Tarjan. It's the time needed to compute the dominator tree. LHC for low high order conjecture, so it's the time needed to compute the low high order. And total old and new is the total time needed by the version from Balzi et al. And from our version, and it includes everything. Especially, it also includes SLT, LHC, and the check done on the Côte side. Under that, we can see that we can really see a difference between the new. We are really slower than before, but actually most of the times come from computing the low high order. So if you subtract the last column from the previous one, you more or less get this one. For the check, so we check more things, but actually it's really cheap. And we can also note that we are pretty slow compared to just computing the tree. So we pay a lot. Part of it comes from data structure in rocks that are not optimal, but also we pay the fact that we do the checking. Okay, so to conclude, we implemented Georgiadis and Tarjan sketch inside Concert SSA, and by extending the previous implementation due to Balzi et al., we now have, and using this notion of low high order certificate, we now have dominance test that is sound and complete. I put that it's reasonably more expensive. I don't know if it is really reasonable, but and actually it's the first complete mechanized certification of a fast algorithm, what is nice in this approach is that we don't really care about what algorithm we use in the unverified part. Actually, since we need some instrumentation, to really compute the low high order, it's not completely true, but it's more or less the case still. And as future work, it would be nice to really try to build something on top of it, and maybe it may reveal that the interface is not the correct one. And since we saw that it's pretty expensive to do that in with the certificate, computing the low high order is expensive, doing the checking, at least with the current data structure, is expensive too. Maybe it's a hint that we should try to do the direct proof of the algorithm. Thank you.
We have time for questions.
So how specialized is your implementation to Concert SSA? If I had my own compiler, would I be able to use your implementation?
All the theory about low high order, I think you can take the dedicated file and move it. I don't think there is anything specific. There is I think the most specific thing is the way that paths are represented in graphs. Then when we check that the order is low high on the parent property, we more or less we can see that we use trees and things like that, which are the internal structure of inside Concert. So probably this part would need to be changed, but I don't think it would be that much of an effort of porting it. And actually, it even have application outside compilers, so it has interested in Zone.
Hello, thanks for your nice talk. So my question is, maybe I missed something. So my question is that whether the computation of the low-high order is verified, or like this order computation can still have some mistake inside.
So the computation of the order itself is not verified, but what is verified at the end is that it's indeed a low-high order. So, I mean, on the unverified part, we just compute a numbering. We just.
But whether this low-high order is consistent with the graph.
Yes, that we need. This is the definition of what it means to be low-high. On this, we need to verify indeed. But this is not what is expensive. What is expensive is computing the numbering, just checking that it satisfies the low-high order definition. It's pretty cheap. Actually, in some of my examples, it's even cheaper than the previous test that was doing strictly less things. So this is a bit mysterious to me. But this is really nothing compared to what is done here.
I see. Thank you so much.
Let's thank the speaker again.